I'm a trained engineer who is just, I'm in awe and deeply admiring of the chemistry of the biological world. Because when you think about how nature creates all these incredible functions, the diversity of transformations that goes into that, and the efficiency and selectivity with which nature can take renewable, abundant resources and convert them into the molecules of life. It's really so inspirational for someone who wants to do chemistry. Now, of course, who does this chemistry? Those are the enzymes, the DNA encoded catalysts, the molecules of life, really, that no human can master. Now, I wanted to be an engineer of the biological world. My training, my PhD, is in chemical engineering, and I wanted to build new versions of enzymes. But no one knew how to do that. We struggled mightily in the 1980s with making mutations in proteins and with the idea that one could sit down and design something that's even better than what nature has provided. Well, luckily, equally awe-inspiring to the chemistry of the biological world is the process by which nature has generated all this diversity, including the enzymes. This remarkable diversity-generating machine, a simple algorithm of mutation and natural selection that is the recipe for all the adaptation, optimization, and innovation of the biological world. It's a really tremendous process that works at all scales, from molecules all the way to ecosystems. Now, we struggled, as I said, in the 1980s to build new biological things, but today, you've heard from Joe DeRisi, we can sequence anything. We can read any DNA. We can write any DNA, right? You can email off to your favorite supplier and get DNA back in the mail. But what we cannot do, this is the problem we struggled with, and the problem we still struggle with today, is we cannot compose it. It's like a Beethoven symphony. Intricate, stunningly beautiful, the work of 3 billion years of evolution, and we're just learning how to hold a pencil. We don't know how to compose, but evolution does. So why not use evolution to move into the future? That's what I'll introduce to you today. Now, I know you are microbiologists who study this tremendous diversity that 3 billion years has given us. But you, I love to offend large audiences, you are relegated to that little green space that's relevant to the biological world. I'm going to talk about evolution into the whole universe of biological possibilities, the things that nature has never tried. Maybe she didn't care about it, or maybe she tried them and threw away. But everything that she has tried all the way back 3 billion years is but a tiny fraction of the universe of possibilities where DNA sequences and life forms could go. This universe is my playground. As the engineer who wants to explore the non-natural world, I have a universe of possibilities. In this universe, think about it, there's the cure to cancer. There's the cure to the energy crisis. There's probably the cure to finding a longer lifetime. There might even be the cure to taxes there. The trick, of course, is finding that. So if we just look at the numbers, you realize just how big a space this is, because even for a single protein, 300 amino acids long, 20 letters in the alphabet, we've got more than all the particles of the universe, even bigger than the US national debt worth of possibilities And the challenge is, if I'm going to be the evolver of proteins, how do I explore this space in a meaningful way, getting something useful, something better than what nature has provided on a time scale that means I don't have 10 to the 9th graduate students or 10 to the 9th years. And look at the numbers. A single mutation in a typical protein, there's thousands of ways to do that. You make just 2 mutations and you have millions of ways, and you start making 3 simultaneously. It's bigger than any screening capability that we can imagine. I often ask my students to read this wonderful short story by Jorge Luis Borges, The Library of Babel. This library contains all possible books of a certain length. And you know there's the true story of your life in that library, but there's lots of false stories in there as well. And the most memorable thing about this library from the human point of view is that the librarians throw themselves off of the balconies of this library in despair because they can never find even a single meaningful book. What does that mean? It means a random assortment of letters that you would find in such a library most of the time doesn't encode anything meaningful. The same is true of most protein sequences. If you just randomly put amino acids together in sequences, the probability that they will encode something useful is infinitesimal. So the challenge for the would-be breeder of molecules, the evolver, is to find something useful in a very short period of time. One solution to this problem came to me reading another remarkable short story, and that's by John Maynard Smith, and I recommend it to everyone. This paper was published in Nature in 1970. And he argued, remember, this is before the sequences of proteins were deposited in all the databases for us to see how evolution takes place. He just had to think about it. Imagine that. He said, for evolution to occur, and I believe it does, it tells us something about the ordering of functional proteins in this vast space of all possible sequences. So consider a functional protein. For evolution to take place, it must lie next to one amino acid substitution away, at least one more functional protein. And that gives you a network in this vast space of mostly non-functional sequences, a network of functional proteins where evolution can take one step at a time. Now, of course, I wanted to make better proteins, not just functional proteins, but things that would solve human problems, things that we could use to replace pumping oil out of the ground, for example. And this becomes an optimization problem. An optimization of fitness. I am the breeder, so I decide who lives and who dies and who goes on to parent the next generation, versus all the ways that you can change or take a step in the sequence space. And if your landscape, if your fitness landscape is very rugged, then, well, most of your experiments send you into crevasses of non-function, and it's not a very fun experiment. On the other hand, if the landscape is smooth, any fool can optimize on such a landscape just by taking the first uphill step and continuing that process until you reach a global optimum. Well, what Maynard Smith told us is that this landscape must be smooth in at least some of its many dimensions. And with that idea, we went forward and evolved things in the laboratory with a simple experimental process where you take something that nature has already given you on a silver platter, on the bottom of your shoe, wherever you can find it, a rare functional protein. You mutate that, making lots of versions. Bacteria then do the hard work. They translate that DNA into mutated enzymes. And then the hard part for the human being is to screen those and decide who has started to acquire the features that might be of interest to you, and that may be highly non-natural. And if you've chosen the right kind of problem and you can measure these properties sufficiently well to capture the small benefits of a single mutation. This is really the trick to effective directing evolution. You can measure those small benefits of a single mutation. Most mutations are deleterious and go straight to the trash can, in the old days at least, in the 90s. Now we put them into the machine learning algorithms. But those rare beneficial mutations get fed back into the process, and you iterate walking uphill in this fitness landscape. Well, yes. All right, so when you have a native enzyme that does its job in the biological world and you ask it to do something new, it's generally less enthusiastic about that. But you can re-optimize it through this uphill process, accumulating one mutation at a time. And it works. It's very reliable. And this is the way all sorts of industrial enzymes are now made. So your laundry detergent has enzymes made by directed evolution, because what self-respecting bacterial enzyme wants to work inside of a laundry machine with hydrogen peroxide and everything else in there? But you can convince it through a process like that to do that. Many of your pharmaceuticals are now made cleanly using enzymes instead of using toxic metals, for example, metal catalysts, and a number of other products are made by this. And so that brought me to a very nice party last December. I was invited to this beautiful city, and you can see all the lights out, and it all looks great until you realize this picture was taken at 3:30 in the afternoon. A little bit dark and cold. It was still fun, and I strongly recommend, if you ever get an invitation to this party, you should go, because they definitely know how to put it on. And I met nice people there. This is Donna Strickland, the first woman in 55 years to win the Nobel Prize in Physics. It was a good year for women scientists. And we are holding not our gold coins, because the Swedes know better than to give the Nobel laureates their gold medals before they leave town, because they're known to leave them lying around. We were given our chocolate coins, and so we're looking pretty, having a pretty good time with our chocolate Nobel medals. Getting back to science. What did we learn through this process of evolution? We learned that proteins can adapt very quickly. That won't surprise you microbiologists, because you know that the biological world can adapt very quickly, taking on new functions with a small number of changes in sequence. And for those would-be designers, it's still very hard to understand how those mutations give rise to new properties. We can see them in the sequence, but understanding how that happens is still a long ways off. We certainly can't predict them. So what I've just told you is a great optimization algorithm. But that's not what I wanted to share with you tonight. I wanted to share with you this idea that evolution is also a great innovator. But how would that simple process that I just described to you, of taking one mutation at a time on this random uphill walk, how could that lead to novelty? And that was a question I asked myself for a long time, because I knew as an enzymologist that you had to have multiple functional groups beautifully positioned to catalyze a reaction and lower its transition state. And it was hard to see how one mutation would give rise to a whole new function. But that's the wrong way to think about it. And maybe you could have helped me do this 10 years earlier if I had spent more time with microbiologists, because microbiologists know that innovation is already there. Enzymes are like graduate students. They can do a lot of things. They may be selected for their ability to work 40 hours a week at low pay, 140 hours a week at low pay, but they can play the piano, they can play sports, they could even do dishes for a living if they had to. Enzymes are just like that. They may be selected for one function, but they have promiscuous or side functions that can be drawn out through this process when the environment changes. And you know many examples of this. So we translated that idea into new enzymes. So here's an example. I'll give you just a couple of examples in this short talk. We asked, gee, a heme protein can activate oxygen, like a cytochrome P450, and insert that reactive oxygen species into unactivated CH bonds. Could they activate a carbene, create a new reactive species, and instead of putting oxygen into a CH bond, could they put a carbene into a CH bond? This is a chemical reaction known to human chemists, but not known in biology. Well, it turns out enzymes are perfectly happy to do that if you just ask them and provide the right precursors to form carbenes. And here's one example of what an enzyme can do if you train it. We can make highly strained carbocycles like bicyclobutanes, which humans have made. They have a really hard time making these because they tend to go pop, 70 kilocalories per mole in strain energy. Here's a transformation from a triple bond that's not even known ever to be catalyzed by iron. But we can convince enzymes, a cytochrome P450 in this case, to take a carbene precursor, make a reactive carbene in the active site, and transfer that to an alkyne, to a triple bond to make cyclopropenes. And if you are smart enough to see who has that incipient capability, we just screen lots of things that sit in my refrigerator, you can find something that has a little bit of activity and evolve that through random mutation and screening over several generations to make the most efficient catalyst ever known for this kind of transformation. But you don't have to stop there, because if you could add a second carbene across the propene's double bond, you could make a bicyclobutane, 70 kcals per mole of strain energy. It's like rocket fuel. And an enzyme will happily do that, and not only do that, but do it inside of living bacteria. So if you just add your precursors to living bacteria, they will churn out, for the price of sugar, bicyclobutanes. As far as I know, nobody cares, because nobody has ever had these stereochemically pure bicyclobutanes in the past. Just goes to show what microbes can learn to do with a little bit of training. Microbes can also learn how to make bonds that are not even known in the biological world. Think about silicon. There's no known organosilicon chemistry in the biological world. Silicates, yes, but carbon-silicon bonds are not known. Odd. Humans make them. There's 50 products in this room that have carbon-silicon bonds. It's a huge industry. It's an industry that never even thought about coming to an ASM meeting, because there was no enzyme ever reported to make carbon-silicon bonds. Well, we go to the refrigerator and we ask proteins that we know as chemists could possibly have a little bit of that activity, and it turns out that a cytochrome C, an electron transport protein from a microbe that you find in a hot, salty pool in Iceland, can take EDA, ethyl diazoacetate, carbene precursor, and insert a carbene across a double bond into the SiH bond of a silane and make a new silicon-carbon bond. And it does it as well as the best human chemist ever reported. This is the wild-type protein. This is a really stable protein because it comes from a hyperthermophile. It's so stable you can even give it to a chemist. They won't even know it's a protein. It's just a powder. It's a magic organosilicon catalyst in the form of a powder. And when I talked about this work in a meeting where people understood something about cytochrome Cs, and maybe some of you know something about cytochrome Cs, somebody in the front row jumps up and said, Francis, but there's no active site in a cytochrome C. All the coordination sites to the iron, heme, are saturated, right? They're all occupied. So where does the chemistry actually happen? In fact, if you do your calculation, you roll the ball over the active site, you get a big fat 0 for the volume. But you know what? Nature doesn't care about your calculations. This is really important to remember. You can talk yourself out of it, and you can wonder why this happens, but it happens, and not only does it happen, it evolves. So you have something that has a little bit of activity, 40 turnovers, beautiful enantioselectivity for this reaction. And by accumulating mutations, you can take it to where it can get published in a snooty journal. It's that good. And if you look at the crystal structure, it has figured out how to build an active site into this protein. Nobody can predict how these three mutations, just three mutations, built this active site, but it is now the most efficient catalyst for this kind of carbene insertion reaction. When we published the paper finally, actually before I published the paper, I always have somebody problematic sitting in the front row. It was the science reporter. And he said, oh, you got to tell me more about this. And you know, students, if you blab too much, you won't get your paper in the snooty journal. You're not allowed to publish by press release. So I said, no, you can't, I can't tell you anymore. You're just going to have to write your story based on what I said. So he completely made up a story, absolutely made up a story. He said we were taking a step towards silicon-based life. This was a great story. Do you see Spock interacting with the Horta? Everybody in the world saw this story. When the paper was published, no one read the paper. They just went to this story. And that was really fun because the paper said nothing about silicon-based life. It just said we could make E. coli that put silicon and carbon together, but they all read the science journalist's story. And so as the paper was published, the story went all over the world. It mutated. Popular Science, bless their hearts, they actually got it right. They said, oh yeah, you know, Arnold's looking for silicon-based life. I don't think that's going to happen. That's really not chemically feasible. I never said it was going to happen, but nobody wants to read 130 pages in your SI of all the compounds that you made. Astrobiology magazine, however, had a different take. Now they said silicon-based life, that grows, and all 17 readers of Astrobiology magazine clicked on this article, making it the most clicked on article for 2017, which was a year after the paper was published. That was fun. And then, you know these guys, this is the intelligent design community, doesn't believe in evolution. They said, okay, this is intelligent design. Oh my goodness. So I'm now the intelligent designer. I'll take that, that's fine. But then by the time you get to the Twitterverse, oh my goodness, I don't know if you can read this, but we were rolling in our, you know, in the lab, we were rolling on the floor laughing, you know, so can my computer now get, yeah, anyway, you don't need to read it, but people have a good sense of humor. Anyway, let's get back to the science. So what's the message here? We have this incredible diversity of chemistry in the biological world. We're all very proud of that. But the chemists, you know, they say, oh, that's cute. They pat me on the head and they say, Frances, that's really cute, the thought that you can use biology to do all this chemistry, but you can't do what I can do. You can't make carbon silicon bonds. Well, you know, if you look at the chemistry, the CX bonds in biology, there's lots to nitrogen, oxygen, sulfur, a few halogens, a few other things, but there's whole swaths of the periodic chart that biology doesn't touch. Well, in 1.5 years, we added 2 whole new elements to that. It's just that either we haven't found it yet, which is a great possibility, or nature hasn't really cared about organosilicons that you use in your hair gels. It's not very useful for the biological world, but it's very easy for her to learn how to do it and do it better than humans do it. Now, everything I've told you about carbenes, you can do with nitrines. This is a story that keeps on giving because evolution is that one-size-fits-all innovation process. And we can make things with nitrines, just the same with carbenes. And this paper was published recently, and I won't go into any detail. But basically, you can feed heme proteins, very inexpensive nitrine precursors, and they will assemble things like betalactams with perfect stereoselectivity in a single step, bypassing the side reactions that flummox human chemists who use small molecule catalysts. Inside the active site of a protein that you have evolved, you can do CH amidation with pure stereoselectivity and 1,000,000 turnovers to make betalactams. You can make a lot of different betalactams. I don't know if they're good for anything, but enzymes will churn them out for you. And they just do it. You just put the precursor in with bacteria and you get your nice powder out at the end. It's really remarkable. Instead of 7, 8 organic synthesis steps, you just have a protein in water doing this, or dried bacteria in water. And not only that, you can tune the protein to make a 4-membered ring, a 5-membered ring, or a 6-membered ring. No human chemist can do that, but biology can. So I want to leave you with this. I hope it's a positive message that we're just scratching the surface of the chemistry of the biological world. We can take this incredible innovation process of evolution and move into a future of chemistry where your imagination could lead to chemical factories of the future based on these remarkable microbial systems that will do it for the price of sugar. And with that, I want to thank a really bright group of people that did all this work. I just go around and get credit for it, which is okay with me. But they stay home and they do the work. And I want to remind you what you already know, that we live in this incredible, who needs the Internet of Things? Here we are in Silicon Valley, right? They all talk about the Internet of Things. We work with the Internet of living things, crowdsourcing for 3 billion years, solving all sorts of problems. We can harness that to solve problems for us. So thank you very much.